This lecture is about the soft margin classifier. So we've already looked at the hard margin classifier, and the points on either side of the hyperplane are to lie at a distance of at least 1 from the hyperplane. If this is the hyperplane, then this distance is 1 and this distance is also 1, from here to this point. So this point is at a distance of 1 from the hyperplane, and this point is at a distance of 1 from the hyperplane also. But what if the points are not separable by a hyperplane, as in this situation? So here I've surrounded the plus points and the minus points with their convex hulls, and the convex hulls overlap. Therefore, the two regions are the pluses and the minuses cannot be separated by a hyperplane. So we must allow some kind of error here. So this is the soft margin classifier, and we would of course like all the points to lie outside this forbidden region. The blue points should lie here, the plus points I mean, and all the negative points should lie here. But we are allowed to have some overlap, like all these points. These points are in the forbidden region. So for that purpose, we create a new primal variable zeta I, which is greater than or equal to 0. And our constraint now is yi times w transpose xi plus b greater than or equal to 1 minus zeta I. Zeta I is our tolerance that addresses the issue of errors when some of the points cross over into the forbidden region and beyond. For the hard margin classifier, we only had yi times w transpose xi plus b greater than or equal to 1. But now we have this minus zeta I as the modification. So zeta I tells us how much xi violates the hyperplane error. So for this point, which is on the correct side and not in the forbidden region, zeta I equals 0. Actually, we'll see it in the next slide. So for these points here, both the plus and the minus, zeta I equals 0, because we clearly have yi w transpose xi plus b greater than 1. In other words, both the plus and the minus points are at distances more than 1 from the hyperplane. Now here, these are these support vectors for the hard margin classifier, and here these are exactly at a distance of 1 from the hyperplane. This is the hyperplane, this distance and this distance, they're both equal to 1. And so zeta I is still equal to 0. But if we move the plus or the minus points closer to the hyperplane, then this zeta I becomes non-zero, as you can see just right now. So here, the plus and the minus, they're closer to the hyperplane than 1. So we have to have a non-zero zeta I. So this distance, let's say this is about 1/3. So zeta I will be equal to 2/3. And here, let's say this distance is about half. So zeta I is also half. So that 1 minus zeta I is half. And in the plus case, 1 minus zeta I is equal to 1/3. So that's why we have, in these cases, these points are on the correct side of the hyperplane, but they are entering the forbidden region, and so zeta I lies between 0 and 1. For points that actually cross over to the other side, like these 2 points, this point should lie on this side, and this negative point should actually lie on this side, because this is the negative region and this is the positive region. But they have crossed over to the other side, and therefore this distance now is, this should be considered as negative, whence zeta I is greater than 1. Yi times W transpose Xi plus B equals 1 minus zeta I, where zeta I in both this case and this case is greater than 1. So this is a summary of what we just saw. For these points, as well as the points that are exactly on the correct side, but not violating the hyperplane, zeta I equals 0. For these points, which are, excuse me, not for these points, but for points like this, which is still on the correct side, and for points like this, which is on the correct side of the hyperplane, zeta I is between 0 and 1. But for the points which are crossing over the hyperplane, like this point here, and this point here, these are on the wrong side of the hyperplane, then zeta I is greater than 1. So this is the objective function for the L1 norm classifier. We simply minimize summation zeta I, where zeta I is a measure of the error. If you look here, this is the boundary of the plus side of the hyperplane and the forbidden region. And we are measuring any point that is a plus that violates our forbidden region. We are measuring from this side of this margin. Likewise, the negative points which are crossing over, we are measuring the error zetas from this side margin. And so zeta I is always greater than or equal to 0. When we do this minimization, we don't have to therefore take the absolute values because they're already greater than or equal to 0. Therefore, our objective function is simply to minimize summation zeta I. We also have an L2 norm classifier where we minimize the L2 norm squared of the zetas, which is summation zeta I squared. Now let's take a look at the Lagrange multipliers. We have two sets of constraints. Now this constraint was associated with the hard margin classifier, except that we have another term here to take into account the violations of the forbidden region. And since these errors, zeta i's, have to be greater than or equal to 0, we have another set of constraints. And so the corresponding Lagrange multipliers are mu I greater than or equal to 0, which corresponds to zeta I greater than or equal to 0 constraint, and lambda I greater than or equal to 0, which corresponds to the earlier hard margin constraint. Now let's take a look at what happens to zeta I and the Lagrange multipliers, the dual variables mu I, zeta I. Now remember the complementary slackness conditions. So here these pair of points are both on the correct sides of the hyperplane and they're not violating the forbidden region. So there is no error, zeta I equals 0. Since zeta I equals 0, the Lagrange multiplier has to be greater than 0. And for this, yi times w transpose xi plus b is strictly greater than 1. So this is greater than 1. So this constraint is greater than or equal to greater than 0. So the corresponding Lagrange multiplier is equal to 0. This is an active constraint. Therefore, the Lagrange multiplier mu I is greater than 0. This is an inactive constraint, so lambda I is equal to 0. Now here, both constraints are active. Zeta I is equal to 0 because there is still no error. These are still on the correct side of the hyperplane and are not yet inside the forbidden region. So zeta I is still equal to 0, the error. And in this case, yi times w transpose xi plus b is exactly equal to 1 because they're both at a distance of 1 from the hyperplane. So this is 1. So both these constraints are active constraints. Whence mu I is greater than 0 and lambda I is also greater than 0. Now here the points have entered the forbidden region and they're still at a distance of less than 1 from the corresponding margin. So this error is less than 1 and likewise this error is less than 1, and so zeta I in both cases is between 0 and 1. And so this is an active constraint now, and therefore mu I equals 0. This is a inactive constraint now, and therefore mu I equals 0. But this is an active constraint because we have this equal to sign now. Therefore, lambda I is greater than 0. Here, zeta I is now greater than 1 because they're on the incorrect side of the hyperplane. Errors are more than 1. Therefore, the first constraint is inactive. The second constraint is active, whence mu I equals 0 corresponding to the first constraint, and lambda I is greater than 0 corresponding to the second constraint. Now let's look at L1 soft margin classifier. We'll look at the primal formulation and then we'll derive the dual. This is the primal formulation for the hard margin classifier. As you recall, we have to minimize half W transpose W, and the constraints are for all points yi times W transpose xi plus b should be greater than or equal to 1. In other words, they shouldn't be at distances closer than 1 from the hyperplane. This is the corresponding formulation for the L1 SVM. I have highlighted the extra terms in blue. So since we also have errors to minimize, so I have this term, and C is a constant times the term is summation of zeta I, which I also have to minimize. So we have to minimize two things simultaneously. W transpose W, half times W transpose W, sorry, plus some weight times summation zeta I. And now the constraints are, since we are allowing some error, yi times W transpose xi plus b should be greater than or equal to 1, this is a plus here, 1 minus zeta I, and zeta I greater than or equal to 0. This is the primal problem for the hard margin SVM. The objective function is half W transpose W, and these are the constraints, one for each point. yi times W transpose xi plus b minus 1 should be greater than or equal to 0. We have a Lagrangian. So the objective function half W transpose W is here, and this is the constraint appearing here, and it's multiplied by the Lagrange multiplier lambda I, and lambda I is greater than or equal to 0. This is the corresponding primal problem for the soft margin SVM. All additional terms are highlighted in blue. Since we have to minimize summation zeta I, the objective function now becomes half W transpose W plus a constant C times summation zeta I. The constraints have to be modified by allowing some error. So yi W transpose xi plus b minus 1 plus zeta I is greater than equal to 0. And zeta I is the error. So zeta I is greater than equal to 0. The Lagrangian is now has 5 arguments. The primal variables zeta i's form a vector zeta, and for these terms corresponding to the primal variable zeta, we have another set of Lagrange multipliers, dual variables, mu's. And so this is the Lagrangian. The first two terms are the objective function and then minus lambda I times this constraint here, and it's exactly the same as the hard margin SVM except the plus zeta I here. And since the zeta i's are greater than or equal to 0, we introduce another set of Lagrange multipliers, the mu i's, and this term also in the Lagrangian, which is negative summation mu I zeta I. Now, this is the Lagrangian rewritten. I've shuffled the terms such that all the terms which have the errors, the zeta i's, are in the third term. And so this is the Lagrangian. And these two terms of the Lagrangian are identical to that of the hard margin SVM. And therefore, the treatment of the stationary conditions and subsequent derivations remain the same as that of the hard margin SVM. We shall only focus on the additions due to the presence of this term zeta I times negative lambda I plus C minus mu I. So taking the derivative with respect to zeta i's, we have minus lambda I plus C minus mu I equals 0, whence lambda I equals C minus mu I. Now both lambda I and mu I have to be greater than 0. Since lambda I has to be greater than 0, greater than or equal to 0, mu I cannot be more than C. And so what are the range of values for lambda I? When mu I equals 0, then lambda I equals C. And when, on the other extreme, when mu I equals C, lambda I equals 0. Hence, this is what we have. Lambda I can only lie in this range, 0 less than equal to lambda I less than equal to C. Lambda I cannot exceed the value C, because if lambda I is more than C, then it implies that mu I is negative, but we also have this constraint mu I greater than equal to 0. Mu I cannot be negative. So this is what it means. When lambda I is less than C, since lambda I equals C minus mu I, we automatically infer that mu I is greater than 0. Which means, since this mu I is the Lagrange multiplier corresponding to zeta I greater than equal to 0, when mu I is greater than 0 due to complementary slackness, zeta I equals 0. And when lambda I equals C, it means that mu I equals 0, which means that zeta I is greater than 0 because of complementary slackness. When lambda I equals C, plug in the value of lambda I equals C here. So mu I is equal to 0, whence lambda I is greater than, zeta I is greater than 0. This is the primal and the dual for the hard margin SVM. And this is the corresponding primal and dual for the soft margin SVM, L1 SVM. So for this C1 transpose zeta, this is the new term that we already saw in the primal for the soft margin SVM, and this was the enhancement to the constraint. Now we just saw that lambda has to lie between 0 and C, each lambda I. So this is the dual for the soft margin SVM. The objective function, the dual function is the same. Y transpose lambda equals 0. It remains the same as before. Summation lambda I yi equals 0. The only change is we only allow lambda to lie between 0 and C. That is the only difference between the hard margin SVM and the soft margin SVM as far as the dual is concerned. Determining the support vectors and the bias for the hard margin classifier was a piece of cake. Now, there's a little complication when we look at the soft margin SVM. The support vectors correspond to all points where lambda is greater than 0 because those points are all used in the classifier. We only discard the points for which lambda is equal to 0 because then we don't have any contribution of those points in the ultimate classifier. So the support vectors will, as before, remain those points for which the lambda is greater than 0. But the bias has to be computed in a slightly different manner. So let's see. So like I said, the support vectors are the ones for which lambda s is greater than 0. Now for these set of points shown here, the error zeta I is equal to 0 because they are on the correct side of the hyperplane and they lie outside the margin. Whence, because zeta I is equal to 0, the Lagrange multiplier mu I is greater than 0. Since this is greater than 0, lambda I is equal to 0. Since lambda I equals 0, these points can be discarded after the training because they are not needed. They are not support vectors. So these points which are on the correct side and lie outside the margin are not support vectors. Now these points shown here are exactly on the margin and on the correct side. So they have no errors associated with them. Still, zeta I is still equal to 0, and from complementary slackness, mu I has to be strictly greater than 0, the Lagrange multipliers. Now, yi times w transpose xi plus b is strictly equal to 1 because these distances from the hyperplane are exactly equal to 1. So we have this expression here, and because this is now a active constraint, lambda I is non-zero. But since mu I is greater than 0 and lambda I equals c minus mu I, therefore lambda I cannot be equal to c either. Lambda I is strictly greater than 0 because this is a active constraint, but lambda I cannot be equal to c because mu I is also greater than 0. So lambda I is exactly between 0 and c. It's not 0, it's not c. 0 is strictly less than lambda I, which is strictly less than c. And these points can be used to find the bias because we have this equality constraint, whence we can multiply both sides by yi, giving rise to W transpose xi plus b equals yi, and we can solve this equation to find the bias. Now these points are still on the correct side, but they are inside the margin, whence we have an error which is between 0 and 1. So since this is not an active constraint anymore, mu I is equal to 0 from complementary slackness. And since we have this as an equality, therefore lambda I is greater than 0. But since mu I equals 0, lambda I equals c. Because again, lambda I is c minus mu I. Now, we cannot use these points to find the bias because we don't know the values of the zeta i's if we solve only the dual. So since we don't know the values of zeta i's, we cannot use these equations to compute the bias. Now, these points have errors which are more than one because they are on the wrong side of the hyperplane. And for these points, since this is an inactive constraint, mu I is equal to 0, which means that lambda I equals c, because lambda I is c minus mu I, and this is the other constraint. yi W transpose xi plus b is 1 minus zeta I. Since zeta I is more than 1, this term is negative, which implies that the point has crossed over to the other side of the hyperplane. So the support vectors are easy as before. All the lambdas, all the points for which lambdas are greater than 0 comprise of the set of support vectors S. The bias is computed from the points for which lambda was strictly between 0 and c. So only those points constitute the set of points for which the bias is to be computed, and this expression here will give the bias. This is the average of all such points. We compute the, instead of taking one point and computing the b, due to numerical reasons, we collect the set of all points for which lambda is between 0 and c, and then compute the bias as the average of what each point yields. And with that, the classifier is ready as usual. Once the b is obtained, the bias is obtained from this expression, then we can do the classification as in the previous case. When lambda s ys xs transpose x plus b is greater than 0, then it's classified as a +1 point. When it's less than 0, it's classified as a -1 point. Now, let's look at multiple class SVMs. So far, we have looked at binary SVMs, which divide points into two classes, pluses and minus. But what if we have more than two classes? In this schematic here, we have three sets of points: the red minuses, the blue pluses, and the green circles. And the simplest method of developing a SVM classifier is through the one versus all method. So what we do is, for each class, we train a different support vector machine and obtain a different hyperplane. And for each class, we take that particular class as the one, and everything else, every other class as the all, and we develop a hyperplane as shown here. And this green band here simply denotes the correct side of the hyperplane. So all the green circles should lie on this side of the hyperplane. That's why I have this green, light green band here. And anything that's non-green should lie on this side of the hyperplane. Then I do the same thing for the other class. This is for the plus classes. This is the light green band denoting that this is the correct side of the hyperplane. All the pluses, the blue should lie on this side of the hyperplane, and everything that's non-blue should lie on the other side of the hyperplane. Of course, there are some errors here. And likewise for the red. And then this is what the set of hyperplanes look like in the space of sample points. And they are dividing the points into different classes. Let's see how. So here is a point, this purple X. We're not sure which class it belongs to. Well, we can see that it's definitely not a blue because it's on the wrong side of the blue. It's on the non-blue side. But which class does it really belong to? Now, what we see is this is the red hyperplane. It's on the safe side of the red hyperplane, and it's on the safe side of the green hyperplane, but it's further away from the red hyperplane. So we take the argmax k, which distance it's furthest away from which hyperplane, and that k gives you the class Y. So this point, the purple X, is furthest away from the red hyperplane, and so it's classified as a red point, red minus. Now, there's one problem with this basic one versus all method. What happens is when we are training each hyperplane, the one side contains a set of points and the all side contains far too many points because they contain points belonging to every other class. What if the number of classes is high? So the number of points on this side would be much higher than the points on this side. And when we do the optimization, the hyperplane would be pushed to the one side, which is not desirable. It will introduce more errors. So in other words, the one versus all method is unbalanced. So one of the proposed solutions was given by Weston and Watkins in 1999 European Symposium on Artificial Neural Networks, and this is what they proposed. So given any point, so this is the distance of the point from its own hyperplane, and this is the distance of that same point xi from any other hyperplane k, where k is of a different class from xi. And so this is the hyperplane corresponding to xi, and this is another hyperplane that does not correspond to xi. And so in order to make xi lie further away from its own hyperplane, we take the difference and impose the restriction that it should be greater than 1. And if it's not greater than 1, then we incur a penalty, zeta ik. So in other words, every point xi should be at least one more than away from its own hyperplane than it is from any other hyperplane. Otherwise, we incur a penalty, zeta ik, and so our objective function to minimize is half of the sum of wk transpose wk plus c times, which is the weight, times this sum k equals 1 to k, where k is not equal to yi of zeta ik, summed over all points. And of course, zeta ik is greater than equal to 0, and the classifier is as in the one versus all. Next, we move on to the L2 soft margin classifier. And What I've shown here is the L2 SVM formulation, the primal, and the dual is very similar in derivation to that of the L1 SVM. The end.